These are the notes on the reaction profiles. We're going to go through 2 examples, and then there is a problem for you to do and submit on Schoology. With these, we're going to kind of put together everything we've talked about with endothermic and exothermic reactions, and then everything from those potential energy diagram notes that you should have completed. With these, you can complete these in any order. We've got the values given to us up above. I like to do the graph first, but you might already be able to see what type of reaction this is based on the numbers we have. So I'm going to start with my graph. I've got energy of reactants is 5 kilojoules per mole. Energy of products is 3.4 kilojoules per mole, and our energy of activated complex is 9.5 kilojoules per mole. And we don't have to make our graphs perfect. I'm going to just add a couple numbers on here so I kind of have an idea of how to space them so they end up in the right spot. So 10, and then I'm going to use 10 because 9.5 is our greatest value. Then we've got a 5 there, and that's going to be enough for what I put on there. So let's go through and put our values on our graph. We need to include these 5 things here. So the energy of our reactants and products, the energy of our activated complex, and the activation energy, and the enthalpy of reaction. So with this, we've got our energy of our, let's start with our reactants. So energy of reactants is at 5. So I'm going to just put a little dot there at that 5. And then I'll connect my dots at the end. And then my energy of my products is at the end. So our reactants is always going to go first. Products is going to go last. So that's at 3.4. So that's farther down. So I'm going to put products here. So there's my energy of my products. I have both of those on there now. And then my energy of activated complex, I'm going to put that on there. That's at 9.5. So I'm going to just putting it close to the 10 is enough. So that's my activated complex. That is there for us. And then once we have those dots, just to kind of mark where we want to start and end, I'm going to use a smooth curve to connect those. Doesn't have to be beautiful, but that's good enough. For our activation energy is how much energy do we have for our reactants, and then up to our products, so how much energy do we need to get to that activated complex. Enthalpy of reaction is the difference between our reactants and our products. And so to do both of those, what I'm going to do is I'm going to draw a gray line. It doesn't matter what color it is. I'm just going to draw a line, and I'm going to end up making this dotted just because it's going to be a reference for me to see, okay, where am I comparing these two? Because both of those are going to be comparing to our reactant energy. So for that first one, our activation energy, that activation energy is whatever we start from the line, that reference line to the reactants, and then we go up to our activated complex. And that's going to be my activation energy. That's where I see it on my graph. And then my enthalpy of reaction is going to be, I'm going to do that in red. That enthalpy of reaction is from our reactants to our products. And so in this case, our reactant line is above. So that delta H enthalpy of reaction is going to be below. And we can anticipate then that that's going to be a negative because it's below, products are below where those reactants are. So I have those on my graph. And now when I'm looking at this, I might be able to go through and answer these. I'm going to calculate these quick. So enthalpy of reaction, if you need to go back to your notes and get your formula for delta H, or I can write it down for us. So our delta H total for our reaction is going to be delta H of our products minus delta H of our reactants. And so I can go up to my numbers above. Well, my products are 3.4 minus my reactants of 5. So what 3.4 minus 5 is negative 1.6. My units are going to be the same as my units that I have in my original energy values, that kilojoules per mole right there. And so that negative 1.6 kilojoules per mole is that delta H value. And so if I want, I can write that on my graph. So that negative 1.6 kilojoules per mole. And we can see now that our delta H is negative, which means that energy is flowing out of the system. And so if energy is flowing out, that means that heat is exiting. This is going to be exothermic. And so that means that heat is a product. Heat is produced. So we're going to put our delta, our heat symbol, which if it's in a reaction, it's change. Or sorry, if it's an equation, it's change, but that means heat. So we're going to put our heat on the right side with our products. And then, so now I've got that chart filled in. And then finding my activation energy. Well, your activation energy is going to be your activated complex minus the energy of your reactants, because we're looking at how much energy does it get from here to here. So we're going to do activated complex minus reactants. And so my activated complex is 9.5 minus my reactants 5, 4.5 kilojoules per mole. With that, if I want, I can write that here. Your activation energy is always going to be positive. So I have those filled in. Now some analysis, kind of putting all of that together. Were the reactants or the products more stable? And if something is more stable, and this is in your potential energy diagram notes, something that is stable is going to have less energy. And so we can look at which of our two values is smaller. So our products is 3.4, that's less energy. And we can see it's lower on our graph. So less energy is going to be our products in this example. And we know it because it has the least amount of energy. All right, last part, if a catalyst were added to the reaction, how would your potential energy diagram change? Sketch this on your potential energy diagram. So a catalyst helps so we don't need as much energy for the reaction to take place. And so my catalyst is going to lower my activated complex energy. And as a result, I'm going to get a lower activation energy with that. And so I'm going to see this, the hump in my graph is going to be lower. But what's not going to change is that my reactant value isn't going to change and my product value isn't going to change. So it's going to start and end in the same spot, but that activated complex, that hump in the middle, is going to be smaller. And we can say with this, what doesn't change are energy of our products and reactants. And then therefore our delta H total also doesn't change, because we can notice that that delta H value stays the same. All right, one more example. If you want to try this on your own, feel free to pause. We've got energy of our reactants is 250, energy of our products is 425, and activated complex energy is 600. So I'm going to just make 600 my max because that's a nice even number. And then halfway is 300. I'm just kind of breaking these up. So I have some reference points. Half of 300 is 150. So that means this one would be 450. So I'm just kind of giving myself reference points. Our goal is just so that we can see whatever is, how they compare to each other, higher or lower. All right, energy of our reactants. I'll put that on there. My energy of reactants is 250. So I'm going to just go a little below that 300. So those are my reactants. My product, 425. So I'm going to put those 425, I'll do right here. So those are my products. And then we've got our activated complex. Energy of activated complex is at 600, so that's right at the top there. And we can kind of start to notice that this one's going to be kind of the other type of reaction that we've talked about, because we can see that our products are now above our reactants. And then to draw my activation energy and my enthalpy of reaction, though, I'm going to put, again, that reference line from my reactants. And so I'm going to just draw a line. I'm going to change it so that it looks like, so I know it's not a part of my graph. So I'm going to just change it to gray. And then that's my reference. So activated complex here is from my reactants up to that activated complex. That's my activation energy. And then my enthalpy of reaction is from my reactants to my products. Now we can see that that is going to be, that delta H is a positive. It's going up from our reactants to our products. And so this one, because we're gaining heat, this is going to be endothermic. Gaining that heat, that means heat is a reactant. We can see our delta H is positive. Our reactants, it increases from our reactants to our products, so it's positive. So that means that energy is flowing into our system, meaning endothermic. We're going to put our heat on the left with our other reactants. All right, enthalpy of reaction, same calculation as before. Our delta H total is our delta H for our reactants minus products. You should use that formula on the test. You don't have to memorize that. But we get 425 minus 250, which is positive 175 kilojoules per mole. And if we want, we can write that number down here because it's that delta H. So positive 175 kilojoules per mole. Our activation energy is going to be our activated complex minus our energy of our reactants. So that is 600 for my activation energy, or sorry, my activated complex minus energy of reactants, 250. So that is positive 350 kilojoules per mole. And our activation energy is always going to be positive. If we want to label the number there. So we have all of that filled in. And then were the reactants or the products more stable, just like we talked about above? More stable is whatever has lower energy. So my reactants are more stable because they have a lower energy. And then if a catalyst were added to this reaction, how would this change? Again, that catalyst lowers our activated complex. I still want to make sure it's above both my products and my reactants. And I can sketch that on my graph. Like that. So that orange line would be my catalyst. And the answer to these questions are the same as the ones we had up above. It lowers our activated complex energy. So that goes lower, which means we have a lower activation energy. So our EA now would just be that smaller line. And we can't calculate that because we don't have enough information about where it actually went to. And then what doesn't change, the energy of our products and reactants doesn't change. So our delta H stays the same. All right, there is one problem for you to do on your own and submit. Hopefully this helped you kind of put together everything we've talked about so far.